All right, looks like we've got a packed house for this one. The next speaker is Dr. Christopher Swenson. He's a computer scientist, programmer, author, and occasional mathematician. He currently works for Capital One as a technical fellow and previously worked for Seed, Simple, Google, and US Department of Defense. The topic today is CPython internals. Pass it over to Christopher. Thank you.
Thank you. Can everyone hear me okay? All right, great. So make sure keys work here. Yeah, the title of this is CPython internals in the VM. It was sort of a thing I did to answer some personal kind of curiosity questions because I'm just a very curious person. So like what happens when CPython starts up? Like, you type in Python, and actually I think a speaker at another conference I was at had a talk that was type Python at the command line, hit enter, what happens? But he went it from a different perspective, but I thought, oh, I'm kind of curious what Python itself is doing when I hit enter and it boots up, and like what's it doing to get ready to execute my code? And how does it actually execute all of that Python code? I am going to say that I'm going to do like a lot of simplifications for the sake of the fact that this is a 30-minute talk. And if you can sort of kind of maybe squint and read C, you should be pretty fine with this talk. There's a lot of code, but all programming languages kind of look the same. So should be fine. We only have a brief 88 slides to get through in the next 30 minutes. And you think I'm kidding, but I'm not. Okay, so yeah, like I said, I'm curious. I am particularly fascinated by like language implementation details. Like the MicroPython keynote this morning was great because it talked about like a lot of like things that I found really fascinating about that, and kind of compared how CPython compares to MicroPython. And I just kind of wanted to understand a little bit more about what's going on to help me in my own coding for performance or for just understanding in general. Okay, so starting off, so CPython, if you don't know like what I say when I mean CPython, it kind of means three things, at least to me. It means a compiler to convert Python to bytecode. So Python has its bytecode, as was mentioned in the keynote, sort of a compact representation of a Python-like set of code. So CPython is one part of it is a program that converts Python that we normally see and love into this bytecode. And this also refers to a VM that actually runs this bytecode. So a particular instance of it, the official Python VM, essentially. It's also a C interface to interact with the VM. So if you want to write Python extensions, they generally go through the CPython interface, C interface, that is. So the VM is the kind of part that I care about the most in this talk. So the CPython VM was specifically designed with kind of like, I think I heard Guido say once, like old technology in mind. It was meant to be very slow and correct, but very easy to like understand and work with, but not going to win any speed awards. And this is why we have alternate implementations of Python as well, like PyPy and things like that are meant more for performance or experimentation, whereas CPython is just meant to be kind of old, reliable. It's also fairly easy to like look into because of this, I think. It's stack-based. This just means that everything in it is based on pushing things onto a stack and then popping them off in certain orders in order to do like mathematical operations or call functions and things like that, as opposed to things like LLVM, which is a register-based, more modern VM. These are a little bit harder to work with and harder to sort of, reason about. And if you're curious, this is a link I could click on. The dis module, if you import dis or go to the documentation for it, has a lot of great documentation on all of the different bytecodes that are out there in the VM and what they do. And it's extremely straightforward to read. I'll give a quick demo of what dis does. It's just dis for disassembly. So I have a very, very short Python little function there at the top. It just adds two numbers together and then returns them minus one. So pretty straightforward, and I've translated this using dis into bytecode just to show kind of what like a little program looks like. So the first thing it does is, well, I'll walk through this in a second to actually like show exactly what it's doing on the stack. note here that when we sort of go into this translation of bytecode, we lose things like variable names. So if you've ever like been kind of frustrated that in your Python program you can't ask it something like, well, what's the variable name that this is associated with? It's because that information gets thrown away when it compiles to bytecode. So all it knows is that it has two arguments here called 0 and 1. And so before we know those are called x and y. So it loads both of those onto the stack. Stacks kind of grow onto the top. And then we call binary add, which just adds the top two things to the stack and pushes the sum of them onto the stack. And like I said, CPython is not particularly smart. And so what it does then is that it then stores it to another variable and then loads it back. Kind of unnecessary because literally this did nothing with those two operations. Like, could have just kept it there. So again, CPython not necessarily making the best choices about what it can. It just is trying to make things as correct and simple as possible. And then I want to return z minus 1, so I push 1 onto the stack, subtract them, and then return them. And return is just another operation. And that's really like, that's kind of how the CPython VM works with its bytecode. It's just a very, very simple language of pushing things onto the stack, operating with things on the top few entries of the stack, and that's it. A few notes, like I said, it does no optimization. There's also no type information. If you look at this, those are just like, put two things down and add them together. Whatever add means. Add could mean something very different for your particular type. Could be strings, could be integers, could be whatever you want it to be for plus. Which means you have to be very careful with things but like plus, because it's not necessarily commutative. If those had been strings, like the order in which you push x and y onto the stack matters a lot. If they're strings and you had gotten them reversed somehow, right, you would get, instead of AB, you would get BA, which is not what you want. It doesn't matter with numbers, matters with strings and other things. So it has to be very careful about the order in which things are kind of pushed onto the stack. Here was a fun thing I learned while preparing for this talk. You can write a very simple Python program. All it does is assign 87,317 variables to 0, 1, 2, so far, and then try to compute the sum of all of them. And this will actually segfault the Python interpreter, like just by adding numbers. Just completely crashes it. It's pretty great. Now, why 87,317? No idea, but 87,316, totally fine. I'm assuming this like overflows some sort of strange like 16 or 20-bit counter somewhere in there, but I couldn't quite figure it out in time for this talk, sadly. But I did dig for it for a while, and it wasn't anything too obvious. Like Python does support like 4 billion variables or something per function, so it wasn't that, and I wasn't going to write that long on the program. But anyways, fun exercise. You can segfault Python just by adding numbers. Okay, so what does it look like for the main loop? Like, how does this bytecode actually get executed is a question that I really wanted to answer. And so there's, in the Python source code, there's a ceval.c, and inside is something called pyeval frame x. And this is the function that actually is like Python. This is like the most Python-y Python thing ever. And just sort of as an aside here, in prepping for this talk, I actually had a very hard time getting my editor to do like being able to like search around the Python source code very easily for some reason. And so I wrote a Python program that takes the Python core source code and generates a static site for it that is all hyperlinked everything together and syntax highlighted. It's called python-xr. It's pretty neat. So I'll go there right now just to sort of demo that. Maybe, here we go. But anyways, the link is in it and also on my GitHub. But so if you wanted to find that one, what was it called? Eval frame x. So it'll do a simple symbol search. It has a list of all the files. If you click on a symbol, it will take you to that particular line in the file, and everything is highlighted. So if I wanted to go to the definition of PyObject and like play around and look at things, very easy to do so. And it's all nice and statically hosted. There used to be a site out there called, I think, LXR, the Linux cross-reference, which was this, but for the Linux kernel source code. So another large code base you might want to kind of paw around with. But it relied on like databases and like magic Perl scripts to be running on some server somewhere. And it hasn't been updated in years. And so I was like, why don't we just use Pigments? Like Pigments has support for all of this. And I just dump a big static site that's like 150 megabytes and put it on GitHub pages and just call it a day. And that's what I did. So a lot of this talk I did by just kind of browsing through the source code on GitHub pages. So this, I can go through this really quickly. I'm not going to actually like go into detail on exactly what's going on. There's a whole bunch of stuff to kind of get go-tos, and apparently not all compilers support giant switch statements for every single opcode, so they have to have some workarounds for that. But if you kind of go down here and get past all this setup for when it's getting ready to execute this, you can sort of see, where is it? Right about, it's a really big function. Because it's basically Python. Here we go. So essentially right here is where the magic happens, and it has like at this point read your Python bytecode, gotten the next instruction, and then it executes that instruction. And it does this. This is basically shorthand for like all the case statements inside of Python. But you could go through here and see exactly how everything in Python is implemented at a bytecode level, which I think it's pretty cool. Okay, so where did my presentation go? Here we go. Right, so anyways, I think that's a pretty neat thing, and that's how I sort of generated the rest of the slides. The rest of this talk, I was going to talk about startup. So again, the question that I initially asked was, what happens when you type Python? What is Python doing, like behind the scenes? Like, just what's going on? So let's kind of play around with that. So the first thing you have to do is find main. So in modules/python.c is where the main starts, and it's a single line. So that's pretty straightforward, so we can dig into what's going on there. You can see a whole bunch of just variable declarations. It's fine, it's got to read a command line, it's got to read maybe a file that you pass in, nothing really shocking there. And if you follow along on the left, there's sort of like a little stack that kind of shows you where we are that I find helpful. So there's like a whole lot more declarations and maybe even some if-defs that I'm skipping over that don't matter. Like if you're on Windows, then it does other things that are kind of awful, but we won't go into those. Mostly because Windows has all sorts of special cases for dealing with things like threads and all sorts of other stuff. So a thing that I do care about a lot is hash randomization. So this was something added, I think, in Python 2.4 or maybe 2.5, I forget, a few years back, 2011, 2012 or so. They had this thing called hash randomization. So it turns out it's a security vulnerability for Python to load dictionaries the same way every single time, because it means, say, if someone could insert query parameters into your web app and control what they are, they might be able to cause drastically awful performance by getting these worst case edge scenarios in your Python dictionaries. And so a tool they did to fix this is called hash randomization. And so there's a few things here that check for that, and I'll get into a little more detail on that in a second. This is just doing some very simple command line parsing to see if you have hash randomization turned on, because it needs to check that really early on before it started to use any dictionaries or anything internally. Yes, there's a link also to this to the original code, the issue that this was brought up in 2011 or 2012. It's a pretty fascinating read. There was a trend of these in a lot of languages going around to try to prevent these awful performance scenarios. The next step is basically, now that we've checked that we need to do hash randomization, or if we don't need to, then we actually go ahead and call it pyrandom init. By the way, I care a lot about randomization. I have a big security and math background, so I'm probably going to talk way too long about this, and I love it. It's fun. It does a very basic thing here, which is it has to figure out how big of a secret to generate, and it turns out the answer is always 8, but there's some weird computation that has to go on. I'm pretty sure it's always 8. It checks to make sure it hasn't already done this, and then if it hasn't, it continues on. Make sure that, it checks to make sure it hasn't already been disabled, and if it has, then it zeroes out the hash. Checks to see if you have a particular seed you want, like if you're trying to get repetitive results, maybe for testing or something like that, there's a way to override that. And otherwise, it just kind of picks a random seed. And then it calls down here, once it actually has a secret to start with, it seeds the random number generator with a very simple, what's called a linear congruential random number generator. So this is essentially, you can take one number and then you generate the next random number by multiplying a big prime in and then adding a big prime, usually primes. And then you take the top few bits of that to sort of be your 8, maybe 8 random bits per 32-bit number or so. There's some little source code there at the top. it's pretty straightforward. There's actually a lot of interesting reasons about why you would only want the top 8 bits and not like the bottom 8 bits, because the bottom 8 bits are total garbage. Like if you think about this pattern here, you're multiplying by an odd number and then adding an odd number, so the last bit, like whether it's even or odd, is going to have a very fixed pattern. It's just going to kind of alternate, and that's not particularly useful for randomization if you have a very predictable pattern. But it turns out the top 8 bits, really good stuff. You want those top 8 bits, much better. I could talk forever about this, but this is just a very simple implementation of that. Okay, so we pop back out, going back to the random init, again checking for a bunch of Windows stuff and VMS stuff, just in case, or it'll just try the default Unix thing of reading dev random for a seed otherwise. Okay, so we're back to main. We've done our initial randomization stuff to randomize our dictionaries and things like that, or our hashes that feed into dictionaries and things. So then we need to check more arguments. -C, this is the run, this particular string as a command in Python. So it needs to look for the -C, and then anything after it needs to know to ignore it, so that it can get it later and then execute that as a Python program. So it does some stuff just to clean up for that. It also looks for -M. -M is the option, right, that says run this module like as the program. So it has to check for that condition as well before it goes on. And then checks a whole bunch of other flags, and then most of them are just setting some global variable, like yes, we want to turn on debugging, or yes, we want to turn on warnings for Python 3, things like that. So I'm just going to skip over those because there's just a ton of them and they don't really matter that much. We need to tell, so now we're further along on our initialization. We need to set the program name, so that makes sense. We need to know who we are. And then, interestingly enough, we then call initialize. So what is initialize? Well, initialize is initialize x1, okay. I don't know exactly what that means. Oh, it means install signalers. So at the very end of this, needs to know to install signal handlers, so it catches like Control-C and stuff like that. So a whole bunch of more declarations. So when it initializes, basically it needs to boot up an interpreter. It needs to boot up a thread for that interpreter. So that's what those two top variables are. And I think that's two of the first things it does. It makes sure that we haven't already initialized. If we have, we don't want to initialize again. It goes ahead and reinitializes random just in case it hasn't been called already. Maybe if you didn't pass in any of those arguments, it may not have been initialized. So it just makes sure it's been initialized there. Boots up a new interpreter. This just really just allocates the interpreter. Like if you look into this code, which we could do in that other tab, PyInterpreter state new, for instance, this is why this is great to have PyInterpreter state new. Like it literally is just checking to make sure you're not passing in garbage, and then it just sets up and nulls out a whole bunch of stuff. Like pretty basic stuff on how to do this. Nothing too fancy. Okay, so back to this. Python thread state, so same thing. It's if we looked at this, it's just basically setting up every thread has to have like a dictionary and a whole bunch of py thread state new. Yeah, so and that calls this function, and that just does the same thing. Again, it's setting up, making sure that you have like recursions, counters set up correctly, and that you have the dictionary nulled out, and it has an thread ID generates that, things like that. So just basic sort of thread initialization stuff is happening there. And then a really interesting thing happens, which is ready types. So ready types is sort of a lot of the core of what I feel like Python boot up is. So the stuff so far is good, parsing command line options and stuff like that. But what we really want to see is this code right here, which is we're going through every single one of the built-in types and booting them up, like getting them ready to start Python code. You have to make sure that your object one is your object class is initialized and int is initialized and all that kind of stuff. So it has to go through all of that. I guess the first thing it does is type itself has to be initialized. Can't initialize type. And then sort of chaining down all the other things in order that need to be called, and then in some very specific order. And so, every single one of these looks like this: type ready, something, and then there's like 100 lines of this. So what exactly does that do? Okay, so type ready. So we're getting a little bit more deep into the stack on the left. It wants to essentially check for, let's see. well, I'll just say this. It checks the base objects. So if you're inheriting from like another class, it has to make sure those are initialized first. So that'll be like one of the first things that does there. It's also, every type has a dictionary built in so that it can do things like find methods. So that'll have to be initialized. It checks to make sure that everything is ready and that you don't have like a null dictionary. It also, interestingly enough, adds in a tracer right here if you have trace reference. It turns out if you like need to hook into everything that happens in Python, like when types become ready, this is the time to do it. So like if you want to add something to every object in Python, you'd want to add it to this piece right here. So there's like that little if-def that tells you about that, which is pretty interesting. So again, we check the base type, hasn't been initialized, and we go ahead and initialize it. We also, I think this might be one of the first times we've seen reference counting. So at this point, Python is like starting, ready to actually start managing its memory and things like that. So we have to make sure that we keep that every object has a reference to its base type and things like that. So yeah, make sure the base is ready, and if it isn't, then then go ahead and initialize it. Let's see here, PyType base, yeah. Just continuing that, initialize any other things that you might be inheriting from. Nothing too fancy there. Make sure that our dictionary is initialized so that we can store things like references to methods. So this is interesting though. At this point, like, earlier in the code that we'd seen, like we're still initializing all of the types. So we might be initializing object or type itself. Can we do this? Can we even create a dictionary at this point? Like, this is something I was kind of curious about. Like, how do you create a dictionary before you've initialized the dictionary type? Like, it turns out that's fine. Obviously, your Python would be completely broken. This is sort of a special case, but they check for, so if you just kind of look through this, it sets up this dummy object and makes sure that basically there's some memory empty for it so that it can initialize an empty dictionary. Otherwise, it has to run like garbage collection, I think, to find one. But essentially, it gives you back an empty dictionary, and that is fine. There's not really anything fancy going on here that references the base class. Nothing that looks like it's going to just break horribly. So I found that kind of interesting. So popping back out, going back to PyType ready. So it needs to go through and check type-specific descriptors. So yeah, I don't actually know what that means. Whatever that means. I don't, like I said, I'm not a CPython expert, so I don't understand everything going on here. But I really enjoy like kind of going through all of this. So let's see here, calculate the method resolution order. So that you need to, I guess if you have multiple, base types that you're inheriting from, you have to like know how to resolve which method calls map to which of your parent objects and things like that. If there are any special flags, I assume this is some Python internal stuff about class stuff that I don't understand. Yeah. Let's see here. Some Python 3K warning stuff here. All bases of statically allocated types should be statically allocated. Yeah, no idea what that means. Like, whatever, that sounds important. I'm glad they're doing it. I guess, yeah, if I had to guess, I'm not gonna guess. That sounds like a bad idea. No idea. Sanity check for, so this is just some error checking to make sure that you're getting things sane. It does check whenever you're writing a type. It looks for the doc string. And if it is there, then it goes ahead and assigns it correctly. So let's see here. More special stuff. This is a literal comment from the code. Some more special stuff. Very helpful. I have no idea what any of this is. Links to each of the base classes, list of subclasses. So you have to sort of chase all of the types around to make sure they all reference each other. And then finally, this type is ready. We have to set a little flag that says it's ready. All right, so we're back now to initialization. A few more things have to be done. So there are some special types like integers and longs and byte arrays, and floats are not like proper types in a lot of sense because they're those special weird built-in not quite typed like primitives, and so they have their own special initializations. I'm not going to go into all of those. It checks for the verbose flags. Now, so this is the end of initialization. So I guess there's a missing curly brace there at the end. But so after that, that's all initialization. That's Python's like basic boot up sequence. So it has to finish running the main method now. Checks for the verbose flag. Checks again, this looks like it is looking to see if you'd previously set the -c to see if there's an actual specific command to run. Or if there's a specific module to run, then it goes ahead and tries to get that loaded and starting to get ready, like sets up the argv so that you know what it is that you're running. It also looks for the inspect flag, which has some special handling. I think inspect is where you like don't read your startup file and you terminate immediately or something like that to like if it's helping like debug getting your program up and running. So it has some special handling there. So again, checks to see if a command needs to be run. I will go into some of this in a second. Again, checks to see if you have a file name that you want to run. So I do want to go into run main from importer because this seems like the next step in initialization is actually running our code. So we've gotten to the point now finally where we've initialized all of our classes, and now we want to see what happens. I want to know how we actually run code. So how do we get to that point at the very beginning where we're like in that big switch statement executing those things? So hopefully I can answer that. So first it calls run main from importer. That just goes ahead and converts the file name into a Python string, and then has to add that to sys.path as part of that. That kind of makes sense. If you think about it, sys.path is sort of like the location where all of your like modules and things have to live, so as to make sure that whatever module you're about to call is already in there. And then it calls run module main, so it goes ahead and runs this as the main. So what does that do? Interestingly enough, if you look at what's going on here, it's importing a Python module called runpy. It's actually executing a Python program to start your Python program, which I'm not really sure how it does that. That's like the definition of bootstrapping. But it seems like, can't you just write some C code that does this? But no, what it does is it loads up the run module as main function from runpy, which we can, again, look up in here if we want. So what was that? It was called run module as main. My mouse. Oh, did I forget to hit enter? There we go. This actually is Python code, so you can actually just see like in order to run your Python code, you have to run this Python code. Yeah. Like I said, I don't understand everything that's going on here, but I think I found that very amusing. And then it has to set the argv thing. And then it actually, once it's loaded that, the actual way it calls is it calls PyObject call. And PyObject call just takes the thing that you just passed in, and right there you can see it's actually like, as part of the compilation process, it creates like a little C function that it points to, and then it literally just calls that. So that's really, and then it has some handling around it to check for like recursive calls and stuff like that. So it can print out better error messages if you crash your stack. So backing back out, decrementing all your reference counters and checking for errors and things like that. I really love comments again like this, like, does this work on Windows? I don't know, why are you asking me? I'm just reading the source code. But I love that I'm not the only one who writes code. Like that you can have something as core as like the main function of Python that has like, does this work on Windows? I don't know. And then just some so checks for the signal handler kind of stuff there. I think that we mentioned very early on. Again, checking for inspection flags. Almost done. We get to the finalize function there, and I think that's it. I think that's Python's boot up now. So that's actually basically the end of my talk. Like, that went really fast. That was a lot of slides in like a short amount of time, and I have no idea. Oh yeah, 26 minutes. Sweet. I know I have a lot of questions because I have no idea what I'm talking about, but I can attempt to answer a couple of questions in this amount of time, and probably won't know the answers. All right. You need to have like a microphone thing to do questions.
Let's thank Christopher. So I think you win the prize for the most code in a presentation.
Right. I have to say, I got so tired of typing these slides that I wrote a Python program to generate my slides. Like, that's when you know that you have too many slides, is when you can't even type them all.
So we'll open it up for questions.
Thanks. So Python comes with an AST parser,
right,
which I've used myself. Presumably this boot up process will invoke that particular parser at some point?
Yes, so there's a whole bunch of stuff that I didn't get into if I had like another hour or so, we could have gone into things like it actually reading the Python code, like parsing it. I think we hinted, the keynote hinted at this, like some of the stages for this, like you have lexical analysis where you take your string of your program and like break it into chunks and then try to combine those chunks using the Python syntax to sort of understand which things are statements and which things are function calls, and then sort of piecing that all together and doing that whole compilation process. And I would love to go into all of that as well. But again, I mostly didn't go into it for purposes of time. But yes, there is an AST module. The Python grammar is very like straightforward as far as language grammars go. Would recommend looking into that if you are interested.
You've gone down the rabbit hole for us to have a look inside CPython. Is there anything you've learned that changes the way you write your regular Python code?
I definitely don't trust Python as far as the optimization as much as I thought I did. Like looking at like the Python bytecode, I always knew it was maybe like a little like loose and like kind of playing it fast and loose, but more like slow and loose. But so now I'm a lot more cautious about that. As far as, you know, understanding how much time is spent like doing kind of like say operations that aren't great. It makes me really interested in some of the optimization work that I heard about going on around MicroPython and trying to optimize the bytecode. I think that sounds interesting. But so I'm definitely a little bit more interested in like alternative implementations like PyPy and MicroPython for performance reasons, and maybe looking into those a lot more. Like I'd love to do this exact same talk for PyPy and MicroPython and all those things and Ruby and whatever. I don't care. I love learning this sort of stuff. So yes. So going back, it does make me think a lot more about embracing alternate implementations of Python.
Anyone else?
Just out of curiosity, and I suspect you'll just go and look into your really cool GitHub thing to find out, but I noticed when it was initializing the types, there was one called a pyframe. Do you have any idea what that is?
I believe a pyframe is whenever you're executing code, it sort of has its own concept of the stack of calls, and each frame is sort of like each. I mean, I think in compiler terminology it's often just called like a frame of reference. Like this is the list of variables that are live in this particular chunk of code. And it's sort of like whenever you get a stack trace, each of those frames is sort of like what each of those levels is. Like, so what function were you calling, what variables are live and things like that. And if you use things like PDB and other debuggers, you can actually inspect those frames. So I think a pyframe is whenever it first boots up, it has to make one of those. And you can look, I think if we even got into the source code, you can look up in pyframe and get the like exactly what is in a pyframe object. Apparently I was curious about this at some point as well and already clicked on this. So pyframe object is this thing here, and it has, again, like some global variables, local variables, some sort of stack stuff going on, like a thread that it's associated with, like what line number it's on. So framey kinds of stuff.
Have you looked into how Python 2 startup differs from Python 3 startup at all?
I have not. I'd be very curious about that. I imagine they're not too dissimilar because this is pretty straightforward and it makes sense, like the kinds of things you have to do and boot up, like initializer types and stuff like that. But I'd be curious. Yes, that is something else I want to look into. But for this talk, I just sort of wanted to freeze it on one particular version so that I could only be so wrong.
All right, last question, then we're out of time.
Were you ever tempted to have a look at how the GIL works?
Oh yeah, so the GIL. No, the GIL is great. I've gone to several talks on the GIL. And I think the GIL is really about when you enter into certain pieces of the code, you have to like grab a particular lock to make sure that other of your Python threads aren't interfering. At this point, I don't think at any point here we actually interacted with the GIL because we haven't got to the point of executing Python code. But I did not get into the GIL into here. Although I'd be very curious to see more. I know like there's a couple of really great talks on like removing the GIL from Python and like all the implications that has, which I love those sorts of talks. This is sort of like why I wanted to give this talk, is in that sort of vein.
All right, any other questions? Grab Christopher offline and let's thank him once again.
Thank you.